3, Atoms and Molecules. Historical background. In the 6th century BC, an Indian philosopher Kanad suggested that matter is composed of very small, indivisible particles. That is,
Parmanu,
which means the smallest particle. Later, in 430 BC, a Greek philosopher, Democritus, postulated that matter is made up of very small particles which were termed as atoms. In 1808 AD, an English chemist, John Dalton, gave a systematic idea about the structure of an atom. His ideas are grouped together and known as Dalton's atomic theory. By the end of the 18th century, scientists proved experimentally that matter exists in the atomic state and the molecular state. Scientists were interested in knowing how matter combined with each other, why they combined with each other, and how they combined. Scientists formulated the laws of chemical combination after performing many experiments involving chemical reactions. Let's do a quick check. Laws of chemical combination. Law of conservation of mass.
activity.
Let us perform a small activity. Take a solution of calcium chloride in a flask labeled A and a solution of sodium sulfate in a test tube labeled B. Tie a thread to the test tube and carefully lower it in the flask. Cork the flask to make it airtight. Now weigh the flask on a balance. It weighs 300.23 grams. Now tilt the flask and allow the contents of the test tube to come in contact with the contents of the flask. Do you observe any change in the flask? Yes. Calcium chloride reacts with sodium sulfate to form a white precipitate of calcium sulfate and a solution of sodium chloride. Now weigh the flask again. Is there any change in the weight of the flask? No, there is no change in the weight of the flask. It again weighs 300.23 grams. What can we say about the mass of the products and the reactants? The mass of the products is equal to the mass of the reactants. Scientists noticed that if chemical reactions were carried out in a closed container, there is no change in the mass. The total mass of the products is equal to the total mass of the reactants. This led to the formulation of the law of conservation of mass. Antoine Lavoisier stated the law of conservation of mass as matter is neither created nor destroyed in a chemical reaction. Law of constant proportions. Proust analyzed the chemical composition of a large number of compounds to determine the type of elements present and the percentage of the elements present in them. He came to the conclusion that each compound had the same elements in the same proportion, irrespective of the source from which it was obtained or the method used for preparation. Based on these observations, he formulated the law of constant proportions. According to the law, in a chemical substance, elements are always present in a definite proportion by mass. For example, water obtained from any source will have the same two elements, hydrogen and oxygen, present. The proportion of hydrogen and oxygen is 1:8 by mass. This proportion will always remain the same irrespective of the source of water. Similarly, carbon dioxide obtained from any source will contain the same two elements, carbon and oxygen. Carbon dioxide obtained from any source will always have the proportion of carbon and oxygen as 3:8 by mass. Let us study some more examples. Copper carbonate prepared in the laboratory or isolated from nature will always contain the same elements, copper, oxygen and carbon. The proportion of copper, oxygen and carbon will always remain 5:4:1 by mass, irrespective of the source of copper carbonate. Dalton's atomic theory. His theory is the basic theory about the nature of matter. According to his theory, all matter, whether solid, liquid or gas or element, compound or mixture, is composed of small particles called atoms. The postulates of Dalton's atomic theory are: matter is made up of atoms. Atoms are the smallest indivisible particles of matter. Atoms of a particular element are all alike, but they differ from atoms of another element. Atoms of each element have a characteristic mass. Atoms are indestructible, that is, they can neither be created nor destroyed. Atoms combine to form molecules. A molecule is the smallest unit of a compound. Dalton's atomic theory was based on the laws of chemical combination. The postulate of Dalton's theory that atoms can neither be created nor destroyed was the result of the law of conservation of mass given by Lavoisier. Since an atom cannot be created nor destroyed, therefore the number of atoms in the products of a chemical reaction is the same as the number of atoms in the reactants. The mass remains the same in a chemical reaction. This is the law of conservation of mass. The postulate that atoms of each element have a characteristic mass was based on the law of constant proportions. The number of atoms, the kind of atoms, and the mass of atoms of each element in a compound is fixed. Therefore, in a compound, the same elements combine together in the same proportion by mass. This is the law of constant proportions. Let's do a quick check. Concept of an atom. Have you ever noticed a mason building walls? When four walls are joined together, a room is formed. A collection of such rooms forms a building, small or big, like a house or a skyrise. Now, when you look up towards these buildings, can you tell? What are the building blocks of this building? Of course, the bricks. Let us consider another example. When we break a large crystal of salt, we get tiny grains. Well, it is hard to see just one little grain of salt. The tiny grains are the building blocks of the large crystal of salt. The building blocks of all matter, of which different substances are made, are called atoms. We know that an atom is very small in size and that an atom consists of the subatomic particles protons, neutrons, and electrons. Atoms are so small that they cannot be seen even under the most powerful microscope. About 1 million atoms stacked up one over the other would roughly equal the thickness of a sheet of paper. The size of the atom is indicated by its radius, which is called the atomic radius. The atomic radius is measured in nanometers. 1 nanometer is 1 divided by 10 raised to 9 meters or is 10 raised to minus 9 meters. Chemical symbols of elements. Dalton was the first scientist to use symbols for elements. He used circles to represent elements. Berzelius suggested that the symbols of elements be made from 1 to 2 letters of the name of the element. Now, we use names and symbols decided by IUPAC, that is, the International Union of Pure and Applied Chemistry. The names and symbols decided by them are used all over the world for international trade. Many symbols are the first letter of the name or the first 2 letters of the name of the element. The first letter of a symbol is always written as a capital letter and the second letter as a small letter or letter in the lower case. For example, the symbol for the element hydrogen is H. Cobalt is CO. Calcium is Ca. Symbols of some elements are formed from the first letter of the name and a letter appearing later in the name. For example, the symbol of cadmium is Cd. Magnesium is Mg. Some elements have Latin, German, or Greek names. Their symbols are derived accordingly. For example, the Latin name for sodium is natrium and its symbol is Na. Iron is ferrum. Its symbol is Fe. Atomic mass. How did scientists weigh atoms? Hydrogen was taken as a standard for measuring atomic masses. Scientists compared the mass of an atom with the mass of hydrogen to determine their relative atomic masses. Hydrogen being the smallest atom, its mass was taken to be as 1 unit. For example, if 1 atom of nitrogen weighs as much as 14 atoms of hydrogen, then the atomic mass of nitrogen is 14 units. Similarly, if 1 atom of sodium weighs as much as 23 atoms of hydrogen, then the atomic mass of sodium is 23 units. Later, carbon-12 isotope was chosen as a standard for measuring the atomic masses. Carbon-12 atom is that atom of carbon which has 6 protons and 6 neutrons in its nucleus. A carbon-12 atom has been assigned an atomic mass of 12 units. The atomic mass of an element indicates the number of times one atom of the element is heavier than 1/12 of a carbon-12 atom. For example, 1 atom of sodium is 23 times heavier than 1/12 of a carbon-12 atom. Thus, the atomic mass of sodium is 23 units, which is the average relative mass of the atom of sodium. 1 atom of hydrogen is as heavy as 1/12 of a carbon-12 atom. Thus, The atomic mass of hydrogen is 1 unit, which is its average relative mass. Let us discuss the average relative atomic masses of some elements. Hydrogen is 1 unit. Carbon is 12 units. Oxygen is 16 units. Sodium is 23 units. Magnesium is 24 units. Calcium is 40 units. Sulfur is 32 units and chlorine is 35.5 units. How do atoms exist? Atoms of few elements like noble gases like helium, neon, argon and krypton, etc. exist in the free state, that is, as single atoms. But most of the elements being chemically reactive do not exist in the free state. They either exist as molecules or as ions. For example, an iodine crystal is a collection of many iodine molecules. These molecules are so tiny that they are not visible by the naked eye. But what is visible is the entire iodine crystal. Similarly, in sodium chloride, the sodium ions and chloride ions, being so tiny, are not visible. But we can see the compound sodium chloride as a white powder which is made up of several sodium and chloride ions. Let's do a quick check. Molecules.
As the basic unit of an element is an atom, similarly, the basic unit of a compound is a molecule. An atom is not found in the free state, but a molecule is found in the free state. A molecule is made up of two or more identical or different atoms of elements. For example, a molecule of oxygen is made up of two atoms of oxygen. Similarly, nitrogen molecule is made up of two atoms of nitrogen. But a molecule of water is made up of two hydrogen atoms and one oxygen atom.
Molecules of elements.
The number of atoms present in one molecule of an element is called its atomicity. The molecules can either be monoatomic or diatomic or triatomic or tetraatomic or polyatomic depending on the number of atoms present in them. Monoatomic molecules. A molecule is said to be monoatomic when it contains only one atom. For example, the noble gases like helium, He, neon, Ne, argon, Ar, krypton, Kr have one atom each in their molecule. So, the atomicity of noble gases is 1, and hence they are monoatomic. Some metallic elements like sodium, Na, potassium, K, magnesium, Mg, calcium, Ca are also considered to be monoatomic. Diatomic molecules. A molecule is said to be diatomic when it contains two atoms. For example, elementary gases like hydrogen, H2, oxygen, O2, nitrogen, N2, chlorine, Cl2, all have 2 atoms each in their molecule. So, their atomicity is 2. Hence, they are considered to be diatomic. Triatomic molecules. A molecule is said to be triatomic when it contains 3 atoms. For example, ozone, O3, has 3 atoms in its molecule, and so the atomicity of ozone is 3 and it is said to be triatomic. Tetraatomic molecules. Phosphorus, P4, has 4 atoms in its molecule, and so the atomicity of phosphorus is 4 and it is said to be tetraatomic. Polyatomic molecules. A molecule is said to be polyatomic when it contains more than 4 atoms. For example, solid sulfur, S8, has 8 atoms in its molecule, and so the atomicity of sulfur is 8 and it is said to be polyatomic.
Molecules of a compound. The molecule of a compound contains 2 or more different types of atoms chemically combined together. Atoms of different elements join together in definite proportions to form molecules of compounds. Let us consider some examples. In the compound water, the combining elements are hydrogen and oxygen. The ratio of hydrogen and oxygen is 1:8 by mass. The atomic mass of hydrogen is 1 and that of oxygen is 16. The mass ratio by atomic mass for hydrogen is 1 and that for oxygen is 1/2. Therefore, the simplest ratio of the combining atoms is 2:1. In the compound carbon dioxide, the combining elements are carbon and oxygen. The ratio by mass of the combining atoms is 3:8. The atomic mass of carbon is 12 and that of oxygen is 16. The mass ratio by atomic mass for carbon is 3/12 and for oxygen it is 8/16. Therefore, the simplest ratio of combining atoms is 1:2. In the ionic compound calcium oxide, the combining elements are calcium and oxygen. The atomic mass of calcium is 40 and that of oxygen is 16. Thus, the simplest ratio by mass of the combining ions is 5:2. In the compound magnesium sulfide, the combining ions are magnesium and sulfur. The atomic mass of magnesium is 24 and that of sulfur is 32. Thus, the ratio by mass of the combining ions is 3:4. In the compound sodium chloride, the combining ions are sodium and chlorine. The atomic mass of sodium is 23 and that of chlorine is 35.5. Thus, the ratio by mass of the combining ions is 23:35.5. Let's do a quick check. Ions. Ions are formed when atoms lose electrons or gain electrons. Sodium ion is written as Na+ and chloride is written as Cl-. Sometimes groups of atoms also give up or accept electrons, forming positive or negative groups of ions. Single-charged atoms are called monoatomic ions. For example, potassium ion K+, magnesium ion Mg2+, nitride ion N3-. A group of atoms that have a net charge on them are called polyatomic ions. For example, ammonium ion NH4+, hydroxide ion OH-, sulfate ion SO4 2-. What does this charge indicate? The charge indicates the valency of the ion. Magnesium ion is written as Mg2+. The 2+ charge indicates its valency is +2. Sulfate ion is written as SO4 2-. The 2- charge indicates that its valency is -2. The valencies of ions are useful in writing the chemical formulae of compounds. A negatively charged ion is called an anion, while a positively charged ion is called a cation. In sodium chloride, the constituent particles are the positively charged sodium ions and the negatively charged chloride ions. Sodium ions are cations and chloride ions are anions. Let us see some examples of monoatomic ions. Positively charged ions with 1+ charge are hydrogen ion, sodium ion, potassium ion, silver ion, and cuprous ion. Negatively charged ions with 1- charge are fluoride ion, chloride ion, bromide ion, and iodide ion. Positively charged ions with 2+ charge are magnesium ion, calcium ion, ferrous ion, and cupric ion. Negatively charged ions with 2- charge are oxide ion and sulfide ion. Positively charged ions with 3+ charge are aluminium ion and ferric ion. Negatively charged ions with 3- charge are nitride ion. Let us see some examples of polyatomic ions. An ion with 1+ charge is ammonium ion. Ions with 1- charge are hydroxide ion, bicarbonate ion, nitrate ion, and nitrite ion. Ions with 2- charge are carbonate, sulfate, and sulfite ion. An ion with 3- charge is phosphate ion. There are some elements which show variable valency. For example, copper shows 2 valencies, that is 1+ and 2+. Copper ion with 1+ valency is called cuprous ion and is written as Cu1. Copper ion with 2+ valency is called cupric ion and is written as Cu2. The Roman numbers written in brackets indicates the valency of the ion. Similarly, the metal ion also shows 2 valencies, that is 2+ and 3+. Ion with 2+ valency is called ferrous ion and is written as Fe2, and ion with 3+ valency is called ferric ion and is written as Fe3. Let's do a quick check. chemical formulae of compounds. Using the valency of ions, we can write the formulae of compounds.
The chemical formula or the molecular formula tells us about the number of atoms present in one molecule of a substance. Consider the chemical formula of the element hydrogen. It is H2. A molecule of hydrogen gas is made of 2 atoms of hydrogen. We can thus say that the chemical formula of an element is represented by writing the symbol of the element with the subscript written near the symbol. This subscript indicates the number of atoms present in one molecule of that element.
Let us determine the formula of potassium chloride. Potassium chloride is a compound made of potassium ions and chloride ions. We shall follow the following steps while writing the formula. First, write the symbols of the potassium ion is K and chloride ion is Cl. Then, write the valencies below the symbols. The valency of potassium ion is 1 plus and that of chloride ion is 1 minus. Now cross over the valencies of the combining ions. The crossover valencies are written as subscripts with the ions but without their charges. Since the valency of both the ions is 1, the formula of potassium chloride is written as KCl. Now let us determine the formulae of water and sodium sulfate. Formula of water. The combining elements are hydrogen and oxygen. The symbol of hydrogen is H and that of oxygen is O. The valency of hydrogen is 1 and that of oxygen is 2. On crossing over the valencies, we get the formula of water as H2O. Formula of sodium sulfate. The combining ions are sodium ion and sulfate ion. The symbol of sodium ion is Na and that of sulfate ion is SO4. The valency of sodium ion is 1 plus and that of sulfate ion is 2 minus. On crossing over the valencies, we get the formula of sodium sulfate as Na2SO4. Formula of magnesium chloride. The combining ions are magnesium ion and chloride ion. The symbol of magnesium ion is Mg and that of chloride ion is Cl. The valency of magnesium ion is 2 plus and that of chloride ion is 1 minus. On crossing over the valencies, we get the formula of magnesium chloride as MgCl2. Formula of silver nitrate. The combining ions are silver ion and nitrate ion. The symbol of silver ion is Ag and that of nitrate ion is NO3. The valency of silver ion is 1 plus and that of nitrate ion is 1 minus. On crossing over the valencies, we get the formula of silver nitrate as AgNO3. Formula of potassium hydroxide. The combining ions are potassium ion and hydroxide ion. The symbol of potassium ion is K and that of hydroxide ion is OH. The valency of potassium ion is 1 plus and that of hydroxide ion is 1 minus. On crossing over the valencies, we get the formula of potassium hydroxide as KOH. Formula of ammonium sulfate. The combining ions are ammonium ion and sulfate ion. The symbol of ammonium ion is NH4 and that of sulfate ion is SO4. The valency of ammonium ion is 1 plus and that of sulfate ion is 2 minus. On crossing over the valencies, we get the formula of ammonium sulfate as NH4 twice SO4. Formula of sodium phosphate. The combining ions are sodium ion and phosphate ion. The symbol of sodium ion is Na and that of phosphate ion is PO4. The valency of sodium ion is 1 plus and that of phosphate ion is 3 minus. On crossing over the valencies, we get the formula of sodium phosphate as Na3PO4. Formula of aluminium chloride. The combining ions are aluminium ion and chloride ion. The symbol of aluminium ion is Al and that of chloride ion is Cl. The valency of aluminium ion is 3 plus and that of chloride ion is 1 minus. On crossing over the valencies, we get the formula of aluminium chloride as AlCl3. Formula of calcium oxide. The combining ions are calcium ion and oxide ion. The symbol of calcium ion is Ca and that of oxide ion is O. The valency of calcium ion is 2 plus and that of oxide ion is 2 minus. On crossing over the valencies, we get the formula of calcium oxide as CaO. Formula of potassium nitrate. The combining ions are potassium ion and nitrate ion. The symbol of potassium ion is K and that of nitrate ion is NO3. The valency of potassium ion is 1 plus and that of nitrate ion is 1 minus. On crossing over the valencies, we get the formula of potassium nitrate as KNO3. Formula of ammonium hydroxide. The combining ions are ammonium ion and hydroxide ion. The symbol of ammonium ion is NH4 and that of hydroxide ion is OH. The valency of ammonium ion is 1 plus and that of hydroxide ion is 1 minus. On crossing over the valencies, we get the formula of ammonium hydroxide as NH4OH. Let's do a quick check. Molecular mass and mole concept. Molecular masses. Let us determine the molecular mass of water. The molecular mass of water is the sum of the masses of 2 hydrogen atoms and 1 oxygen atom. Therefore, the molecular mass of water is equal to 2 multiplied by the atomic mass of hydrogen plus 1 multiplied by the atomic mass of oxygen. We know that the atomic mass of hydrogen is 1 unit and that of oxygen is 16 units. This is equal to 2 multiplied by 1 plus 1 multiplied by 16. Therefore, the molecular mass of water is equal to 18 units. Molecular mass of carbon dioxide. The molecular formula of carbon dioxide is CO2. The molecular mass of carbon dioxide is equal to the atomic mass of carbon plus 2 multiplied by the atomic mass of oxygen. This is equal to 12 plus 2 multiplied by 16. Therefore, the molecular mass of carbon dioxide is 44 units. Molecular mass of calcium oxide. The molecular formula of calcium oxide is CaO. The molecular mass of calcium oxide is equal to the atomic mass of calcium plus atomic mass of oxygen. This is equal to 40 plus 16. Therefore, the molecular mass of calcium oxide is 56 units. Molecular mass of nitric acid. The molecular formula of nitric acid is HNO3. The molecular mass of nitric acid is equal to the atomic mass of hydrogen plus the atomic mass of nitrogen plus 3 multiplied by the atomic mass of oxygen. This is equal to 1 plus 14 plus 3 multiplied by 16. Therefore, the molecular mass of nitric acid is 63 units. Molecular mass of magnesium chloride. The molecular formula of magnesium chloride is MgCl2. The molecular mass of magnesium chloride is equal to the atomic mass of magnesium plus 2 multiplied by the atomic mass of chlorine. This is equal to 24 plus 2 multiplied by 35.5. Therefore, the molecular mass of magnesium chloride is 95 units. Molecular mass of sodium chloride. The molecular formula of sodium chloride is NaCl. The molecular mass of sodium chloride is equal to the atomic mass of sodium plus the atomic mass of chlorine. This is equal to 23 plus 35.5. Therefore, the molecular mass of sodium chloride is 58.5 units. Molecular mass of sulfuric acid. The molecular formula of sulfuric acid is H2SO4. The molecular mass of sulfuric acid is equal to 2 multiplied by the atomic mass of hydrogen plus the atomic mass of sulfur plus 4 multiplied by the atomic mass of oxygen. This is equal to 2 multiplied by 1 plus 32 plus 4 multiplied by 16, which is equal to 98. Therefore, the molecular mass of sulfuric acid is 98 units. Molecular mass of potassium nitrate. The molecular formula of potassium nitrate is KNO3. The molecular mass of potassium nitrate is equal to the atomic mass of potassium plus the atomic mass of nitrogen plus 3 multiplied by the atomic mass of oxygen. This is equal to 39 plus 14 plus 3 multiplied by 16, which is equal to 39 plus 14 plus 48. Therefore, the molecular mass of potassium nitrate is 101 units. Molecular mass of hydrogen sulfide. The molecular formula of hydrogen sulfide is H2S. The molecular mass of hydrogen sulfide is equal to the atomic mass of hydrogen multiplied by 2 plus the atomic mass of sulfur. This is equal to 1 multiplied by 2 plus 32. Therefore, the molecular mass of hydrogen sulfide is 2 plus 32 equals to 34 units. Formula unit mass. We know that ionic compounds do not consist of molecules, they consist of ions. Therefore, we do not use the term molecular mass for ionic compounds. Instead, we use the term formula unit mass to determine its mass. The formula unit mass of an ionic compound can be determined using the formula of the ionic compound. For example, the formula unit mass of sodium chloride, NaCl, will be the sum of the atomic masses of sodium, Na, which is 23 units, and chlorine, Cl, is 35.5 units. The formula unit mass of sodium chloride is 58.5 units. Mole concept. We know that a dozen is a collection of 12 substances, a century is 100 substances, and a gross is 144 substances. As we use the terms dozen, century, gross, etc. to express a certain quantity of a substance. Similarly, a mole is a word used to describe a collection of particles, that is, atoms, molecules, or ions. Let us define a mole. 1 mole of a substance is equal to its atomic mass or molecular mass expressed in grams. The atomic mass expressed in grams is the gram atomic mass. The molecular mass expressed in grams is the gram molecular mass. The atomic mass of sodium is 23 grams. Therefore, 23 grams of sodium is equal to 1 mole of sodium atoms. Similarly, the molecular mass of oxygen is 2 multiplied by the atomic mass of oxygen. This is equal to 2 multiplied by 16 equals to 32. So, 32 grams of oxygen is equal to 1 mole of oxygen molecule. Avogadro experimentally found out that 1 mole of any substance always contained 6.022 into 10 to the power 23 particles. This number is called the Avogadro's number, denoted by N0. That is, 1 mole of a substance is equal to 6.022 into 10 to the power 23 particles, that is, atoms, molecules, or ions of the substance. Let us study a few examples. How many molecules will be present in 2 grams of hydrogen gas, that is H2? 1 mole of hydrogen molecules is equal to the molecular mass of hydrogen. This is equal to 2 grams. We know that 1 mole of hydrogen molecules contains 6.022 into 10 to the power 23 hydrogen molecules. Therefore, 2 grams of hydrogen gas will also contain 6.022 into 10 to the power 23 hydrogen molecules. What is the mass of 1 atom of hydrogen? The gram atomic mass of hydrogen is 1 gram. The gram atomic mass of hydrogen will contain 6.022 into 10 raised to 23 hydrogen atoms. Therefore, mass of 1 hydrogen atom is equal to 1 divided by 6.022 into 10 raised to 23 gram. This is equal to 1.66 into 10 raised to minus 24 gram. How many molecules are present in 42 grams of nitrogen gas, that is N2? The atomic mass of nitrogen is 14 units. Nitrogen is a diatomic molecule. The gram molecular mass of nitrogen is 2 multiplied by 14, which is equal to 28 grams. How many moles is 42 grams of nitrogen gas? the number of moles of nitrogen is equal to the mass in grams divided by the molecular weight. This is equal to 42 divided by 28 equals to 1.5 moles. Since 1 mole of nitrogen molecules contains 6.022 into 10 to the power 23 nitrogen molecules, 1.5 moles of nitrogen molecules will contain 1.5 into 6.022 into 10 to the power 23 molecules. Let's do a quick check.